Good morning. I'd like to talk to you about numbers, because numbers are really important in computing. Computers are machines that can manipulate numbers, and that is literally all that they can do. Machines cannot do anything except manipulate numbers, and yet somehow they seem to be in the middle of almost everything that humans do today. So how is that possible? It's because numbers are so incredibly powerful. And I want to look at the history of numbers. So numbers begin with fingers. Now, fingers are actually much older than numbers. Fingers are a multi-use technology. They were really good at holding onto branches in trees and picking and eating fruit. And eventually we figured out that you could also count with them. But before that, the climate changed and we had to drop out of the trees, had to walk around looking for other sources of food. And it turned out fingers were also really good for manipulating tools, for digging tubers out of the ground and mashing them with rocks because they're too tough to eat with our cute little monkey teeth. And as we did this, we began to level up. With the next set of upgrades, we were able to make very sharp knives out of volcanic glass and to manage fire so that we could cook the food, which increased our availability of food sources. And eventually we learned to plant stuff and grow it ourselves so that we didn't have to walk around all the time looking for food, that we could make it in the place that we were. And eventually that leads to civilization. So all as a result of having tools. As we start to grow, as we have little communities which grow into cities, we need to manage it, and it becomes too much to manage on our fingers, or in the simple note-taking devices we had, like making cuts on a stick, or marks on a wall, or knots in a cord. We had to invent accounting. We had to figure out a way to keep track of all of the stuff that goes on in a city-state, and it gets really, really complicated. And in order to make sense of all of the numbers that we were accumulating, we had to invent writing. Writing, I think, is the most important thing that humans ever invented, maybe ever will invent. Writing is what ultimately made all of this possible. And we use writing for letters and literature and laws, but it starts with ledgers. So writing, this really important discovery, happens not once, but 3 times. First time in the Fertile Crescent, second time in China, and the third time in America. Unfortunately, that civilization doesn't survive the European conquest. So each culture had their own way of dealing with numbers. So I like Egypt, so I'm going to start with them. They have a stick which represents 1, a coil of rope represents 100. I really like that they have a symbol for 1,000,000. It's a guy saying, it's a But it doesn't mean it's a whole lot. It means exactly 1,000,000. So having a symbol which means exactly 1,000,000 is demonstration of some real mathematical sophistication. So the Egyptians taught their system to the Phoenicians, who were these amazing traders. They sailed all over the Mediterranean and into the Atlantic, trading with people. And they found that the Egyptian system was too cumbersome. And so they made it more simple. It was sort of like hieroglyphics, the good parts, where they reduced all of the Egyptian system down to a couple dozen characters and had those characters representing sounds, much as the Egyptians did, although they also had them represent pictographs and ideas and other things. And they taught their system to the people that they traded with. So the Greeks adopted their system. They abandoned the system they had been using and adopted this one. And because the system had 27 characters in it in ancient Greek, they mapped it onto their numbers. And so they have letters which represent 1 through 9 and 10 through 90 and 100 to 900. And so you'd have things which could be words, which could mean a word, or it could mean a number. They taught their system to the Romans. The Romans got a lot from Grecian culture, but they sort of kept their numbers based on the original Egyptian model, where they use I to represent the stick, which represents 1. X is a bundle of sticks tied together, representing 10. I don't know how they got to C, but well, I guess it does look like the coil of rope, doesn't it? I just realized that. But they wanted to make it more compact because, as you saw, the Egyptian system could get kind of big. So they came up with symbols representing half of things. The V they got by taking the X and cutting it in half. So half of an X is a V. They did a similar thing to the C, cut that lower half as an L. And they also came up with characters which were subtractive. In the earlier systems, they were all additive. You keep adding symbols, and as you add things, things get bigger. This system is subtractive. So if you put a small thing in front of a big thing, it subtracts from the big thing. And it worked. You know, they had an empire that ruled a big chunk of the world for a long time, although I think this is a really difficult system to add numbers in, even harder to do multiplications. Meanwhile, in China, they came up with a really elegant system which writes numbers in a way that's very similar to the way we speak numbers. So they've got the characters for 1 through 9, and it seems almost a universal thing that a stick represents 1, and they did the obvious thing, 2 sticks is 2, 3 sticks is 3, which is brilliant. I don't know how they got to 4. And then they've got modifiers for 10, 100, 1,000, and then further modifiers, which are similar to the ones that we do. You know, we'll count and then we'll put 1,000 behind it. We don't have to invent a completely different set of symbols. And that worked really well, and they got some big numbers too, also very sophisticated. Then in India, they do something really different. So they come up with a positional system, which means they just have one set of digits that work in all positions, and they have a 0 to indicate numbers that are missing from a position. And they taught their system to the Persians, who called it the Hindu system, and the Persians taught it to the Arabs, and the Arabs taught it to the Europeans, who called it the Arabic system. And it's really lovely. So all of these systems work. So this is the same number represented in all of these systems. And sometimes people want to say there is an historical inevitability that we would have had to have gone to this. And I don't think that's the case, because all of these states were extremely successful, and it worked. And looking at it from the point of view of modern computing, computers could work equally well with any of these. So it's hard to say that any of these has a big advantage over the others, except for the Indian system, not in the way it represents things, but in the way it helps us to think about things. For example, we have the number line now, and we can apply the number line to our numbers. So the position on the number line tells us what power of 10 this thing represents. And so what falls out of that is a system of polynomials. And polynomials turn out to be a really important thing in mathematics, and it kind of falls out of the Indian system. And then the idea of negative numbers fits into this as well. And the other systems had subtraction, but they didn't have negative numbers. And, you know, because minus 2 loaves of bread, what does that mean? It was just, but with this system, you can think about what minus 2 loaves of bread. It's not a ridiculous idea. It's actually something that's meaningful, that we can have credits and debits, and that's actually a useful thing. And then once we have negative numbers, we can then drive the number line in the other direction, and that gets us to the real numbers. And the other systems had ways of dealing with fractions. Like the Egyptians had this amazing system that was all based on simple reciprocals. So you could add 1/2 and 1/3 and 1/4 and 1/5 and 1/6 and 1/7. Whatever value you wanted, you've got these little things, fractions, and you put them together. And they had complicated tables for managing that kind of addition. And so their fractional system worked on a completely different principle than their integer system. But with the Indian system, we can get to a system that works the same. It's just, you have to mind where the decimal point goes, otherwise everything works the same all the time. That's kind of neat. When the Indians were writing their numbers, they needed a place to indicate where the 0 power thing was, and they used a mark above that digit to indicate it. When it moved to Europe, it turned into a little mark that was after the unit digit, or the 0 column digit. And unfortunately, the world has not decided which of those we're going to use. In some countries, they use the dot, and some use the comma. And in whatever country you're in, that works just fine. The problem is when you do international stuff, which is a problem on the internet because everything on the internet is international. Everything can go everywhere. And so something could show up, and does that mean 2 or does that mean 2,000? There's no way to know. And if it's a money value, that could be a big deal, right? So I predict eventually humanity will decide we should have one of these. There's this thing about people that if we're given a choice, half of us will choose one thing and half of it will choose the other, even if there's no good reason to prefer either one, and we will fight about it and create huge problems for ourselves when there is no advantage to either system. So there's not a logical argument as to which one should we get rid of, but we should definitely get rid of one of them, right? And I think the one we're going to get rid of is the comma, that the one that's going to win is going to be the dot, and it's going to be because of you. That in the future, all numbers are going to go through your software, and because of the bias of your programming languages, you'd really prefer the whole world to get behind the dot. So all of the number systems we looked at used base 10, including the Chinese system, which was not influenced at all by all of the others. So you ask, how did Egypt come up with the same base as China? It was sort of the same way that they both came up with writing. They just looked at what was at hand and go, 10, yeah, that's a good number. And so we all use 10, although not everybody in the world used 10. There are some people who used 20. For example, the American system used 20. How do you get to 20? And 10 of those. And it's much more cumbersome, it seems to me, as someone who didn't grow up with that system, but it worked. And there was a high civilization in America that used base 20. And there were other places in the world as well. Another very popular base was 12. And how do you get to 12? Again, 10 and then 2 of those. And we still see 12, right, in our timekeeping. We've got 12s all over the place, which is really annoying. And then in dozens and other places, 12 shows up quite a lot. And then 60. So in Mesopotamia, they had base 60. You go, what were they counting? How did they get to 60? So what I think happened was, as the big city-states start to form, they're annexing other countries and cities that are nearby. And in the Fertile Crescent, there were some societies that were using 10 and some that were using 12. And the new king says, got to make it all work. So they put together a standards committee. And that committee's job is to figure out, are we going to do 10 or 12? What are we going to do? And they can't agree, right? Because obviously there's a huge advantage that society wants us to have one, that having 2 sets of numbers, if we have to exchange stuff, it just gets way too complicated. We all win if there's one, but nobody wants to lose by it being the other one. And so they did what standards committees very often do. They came up with a mutually disagreeable compromise. Okay, nobody wins, we both lose, so what we'll do is we'll find the least common multiple of 10 and 12, and that becomes the standard. So it's awful, but it worked. I mean, there was a high civilization going on there. And it still survives, right? Our timekeeping is still based on 60. Our geographic location is based on 60, which is really annoying. If you ever had to do computation on time or on geography, It's really annoying. This should have been the base 10 thing, right? Some stupid committee 5,000 years ago couldn't agree, and we're still stuck with it. If a standards committee gets something really wrong, it can go on forever. So the next breakthrough is that recognizing that we could apply any base to this system. The Indians used 10, but they could have used 12 or 20 or 60 or anything. It turns out another really interesting base is 2, because this is the one that the computers like. And if we can build stuff out of base 2, we can build digital circuits, which eventually will power the world. So when you're making numbers out of bits, you have the problem of how are we going to represent the negative numbers? So clearly you need a sign bit, and there are 3 popular ways of using the sign bit. The first is called signed magnitude, where we'll simply allocate 1 bit. It could either be at the front of the number or at the end, doesn't matter. And if it's either 0 or 1, the number will be positive or negative. And again, it doesn't matter. You just pick a convention and it'll work. One bad thing about signed magnitude is that you can get 2 values for 0. You can get a 0 and a negative 0, which is nonsense, but it's possible. Another way of doing it is called 1's complement. You also have a sign bit, but it works a little differently. So the way you make a negative number is by flipping every bit. So every bit that was a 0 becomes a 1, every bit that was a 1 becomes a 0, and that's a negative number. And that works. There's one bit of trickiness. If you add numbers and there's a carry that falls off the top end, you have to take the bit that fell off and add it back onto the low end again. But that's an easy thing to do. But again, it has the problem that there are 2 zeros. Then the thing that's used in most of our systems today, so all of our ints use 2's complement, and we make a negative by flipping all of the bits and then adding 1. So the end around carry happens at the time we do the negation, not on every add. So the circuitry gets a little bit simpler. There's only 1 0, which is good. Unfortunately, there's an extra negative number. And it's a really nasty negative number that if you try to take that negative number and make it positive, it stays negative. And so that's a potential source of errors. So I think what we should have done in these representations, and we still could do in some better future computer architecture, instead of having the extra value that doesn't mean anything, we could have it mean nothing, right? We could have it be the null value, the thing that says, this is not a number, this is something weird and different, because often we need that information. And in those representations, there's no place to put it. So you can see examples of this kind of type error in Java and in JavaScript. JavaScript didn't need to have this error. Java did because it has a really crappy type system. So in Java, you can, you're searching for the index of Z in ABC. It's not there, so you want to return something which says this is meaningless. You can't find it. And Java had no value to represent it, so they picked -1, which is awful because -1 is an int just like all of the other ints. So if you take that result and try to put it in a calculation, you could very easily end up with something that's bad. Whereas if it were a null value, then that null value would get fed into the computation and would cause that computation to fail. So getting software to fail early generally means we're going to find the problems and correct them. That would have been a better thing. JavaScript could have done that because JavaScript has a much better type system than Java. It actually could return null in this case, but it didn't. So let's talk some more about types. So in an ideal system where you have a type called int32, you know what that is. It's ints with 32 bits. If you add 2 int32s together, what is the type of the result? Anybody? No, the answer is int33. int33, because a carry can occur. Yeah, overflow. And so the correct answer is int33. Any system which ignores that overflow has an invalid type system, obviously, right? So let's ask another one. What is int32 times int32? Any guesses? Someone said int64. No, it's int63. Int63 is the correct answer, but very close. You came much closer than Java did. Java still says it's an int32, which means horrible errors can potentially happen from every add, every subtract, every multiply, which is, we're trying to write programs that are correct and useful, and how can you do that? How can you have confidence in the system when your numbers can go wildly wrong? When you have a type system which actually enforces the likelihood of errors occurring. So the problem is overflow, that all of these operations can potentially produce more bits than are available for storage. So that raises the question, what should have happened? Obviously, Java did the wrong thing, but what would be a better thing? So there are a number of schools of thought. There's not a single right answer. One is that you should store a null value or some other thing that said this computation went wrong. So instead of storing the wrong thing, you represent something that says, no, this is actually wrong. That's a reasonable thing to do. Another is you store the largest number that fit. This is called saturation. This is sometimes done in signal processing and computer graphics, but you don't want to do this in financial applications, right? That would not be good. Another thing you could do is have a fault. Throw an exception, allow some higher level of software to decide we have to deal with this failure. But if instead what you want to do is maximize the likelihood of the creation of errors, you want to discard the most significant bits without notification. And in fact, that's exactly what Java does, and most of our languages do that. JavaScript does not do that, to JavaScript's credit, but most of the other languages do. So the very first computers, the first von Neumann machines that were built just after World War II, these were machines that were designed and built by mathematicians who wanted to do mathematics on these computers. But they were integer-only machines. But the mathematicians aren't satisfied with integers. They want access to the real numbers. And so they came up with a system of scaled arithmetic, where a scaled value is determined by an integer value times a scale factor. And figuring out the scale factor is really hard. It makes addition harder because you can only add two numbers together if they have the same scale factor. So if you're trying to add two things that are scaled differently, you have to conform them somehow. Multiplication, there's a division that's implied by that in order to remove or prevent the squaring of the scale factor. Division similarly requires another multiplication in order to prevent the scale factor from getting factored out. And finding the ideal scale factor, the one that gives you the most precision without danger of overflow, is hard. So some genius came up with floating point. And the guy was a genius. He was in England, I think maybe at Cambridge. Came up with the idea that we represent a number as two numbers. One is the thing that contains all the digits we're interested in, and the other is where the decimal point is within that string of digits. And it was great. The only problem with it was that it was implemented in software and it was really slow. So there was interest in putting that into hardware. But it was hard to put into hardware in the 50s because hardware was still being made out of vacuum tubes, and these operations required division by 10, which is kind of a complicated circuit. And so they decided that this decimal floating point was too hard because that 10 just was hard to implement. So they came up with binary floating point, which had a basis of 2. And the advantage of binary floating point was instead of having to divide by 10, you do a shift, and a shift is virtually free. So eventually they came up with this format. And I think virtually all modern binary floating point systems look like this. So there's the number that contained all of the bits. That's called the significand. Sometimes it was called the mantissa, but some mathematicians get really upset if you call it a mantissa. And they split the sign up so it's in two pieces. The sign goes at the most significant part of the word, and the rest of it goes here. And it's scaled in a funny way so that instead of just being a string of bits, it's now a fraction between a half and almost 1. And as a result of that, when the thing is normalized, the 1 bit will always be at the top end. And on some implementations, it means we don't have to store the top bit because we know it's always going to be 1, and so we kind of get a free bit. And then there's the exponent, and the exponent, again, is telling us where the binary point is. And it's also represented in a weird way. And the reason they do that is so that they can do an integer comparison on numbers, to see if one number is less than another number. They can pretend that they're integers. And in this encoding, that works. And in the 50s, that made a lot of sense. The 50s was a long time ago. So the problem with this format is that it cannot, because the basis is 2 and not 10, it cannot exactly represent the decimal fractions. And we see this in JavaScript all the time. 0.1 plus 0.2 is not equal to 0.3. And I think this is awful. I mean, we're in the 21st century and we still can't add two numbers together correctly. I don't think this is a little thing. I think this is a big thing. And it comes out of the things that we did a long time ago, over half a century ago, and have not revisited those decisions since then. So how did this happen? So we'll put this number on the number line, and we can see that 1/16 and 1/32 don't quite get us to 0.1, so we're going to need some more digits. So we string out more bits, and we can see that it doesn't ever conclude, right? In base 2, a tenth is an infinitely repeating fraction, similar to 1/3 in base 10. And so we go 0, 0, 1, 1, 0, 0, 1, 1 to infinity. But we don't get an infinite number of bits, right? Our systems have to be finite, so we have to truncate this infinite bit stream. And if we truncate after a 1, it means we lose all of the ones that follow, and our number is going to be too small. And if we truncate in front of a 0, or in front of if we truncate after it, if we do it the other way, then we round up, and we end up with a number that's a little big. It's impossible to ever get the right number, just not possible. And that breaks the associative law. The associative law holds only if all of the inputs, outputs, and intermediate results can be represented exactly. But we don't, and so this fails. 0.1 plus 0.2 plus 0.3 is not equal to 0.1 plus 0.2 plus 0.3. I think that's pretty awful. It means the order in which you add things is going to determine what the result is, which is wrong. So business users rejected that immediately. They said, we cannot do this. We cannot use binary floating point because we have decimal values that have to add up exactly. We can't sacrifice the associative law, or we can go to jail. So that divided computing into two branches. There was the Fortran, or the scientific branch. They used Fortran as their primary language, and they used binary floating point. And there was a business school that used COBOL and BCD. BCD stood for binary coded decimal. That was a system where they would use 4 bits to encode digits. So it's not as efficient as binary floating point, or even decimal floating point, but it's easier, because instead of dividing by 10, you do a shift of 4 bits. That's almost free, so that was done. But since then, we have forgotten what we knew in the 50s, and we're now using binary floating point everywhere, even in places where it's completely unacceptable. One of the things that's hard about implementing binary floating point is doing text conversion into the binary format and back, because there is not an exact one-to-one mapping from one set to the other set. And so there's weirdness. So a floating point library that does that conversion needs to be correct, optimal, and unsurprising. And that turns out to be really hard to do, computationally expensive. If you look at the performance of JSON, for example, JSON is a very efficient data format because it does very little work. The place where it does most of its work is in converting numbers into strings and back. And that's the most computationally expensive part of JSON processing. It's because of this stuff. So most programming languages are a confusion of faulty number types. So when you're programming in Java, every time you're going to create a parameter or a variable or a property, you have to ask byte, char, short, int, long, float, or double. Which one? You have to pick it. And if you get it right, then hooray, it'll work. And if you get it wrong, program's going to fail. And it's unlikely that your tests are going to find the case where it fails, because your tests are all written assuming that the type system is working for you. And so the tests cannot be looking for places where the type system is going to fail. And the value of having made that choice is that you've saved some bits. The approach that JavaScript takes is everything's double. You don't get a choice. It's all double. And the cost of that is some bits are wasted. What is the cache value of the bits that were wasted? It is 0. And it just doesn't matter. In the 50s it mattered, not so much anymore. And this stuff can cause serious errors. The biggest single error I found was the Ariane 5 failure. Anybody remember that? The European Space Agency built this wonderful rocket ship, and they sent it up, and it explodes a few seconds after takeoff. And the control software is written in Ada, but here I've translated it into Java. This is the statement that failed, that they took a double horizontal bias and they truncated it into a short, and it overflowed and confused the guidance system, and boom. It's estimated the cost of that failure was $500 million. Now, you probably haven't had any bugs worth that much yet. But you could. I mean, they could be waiting out there. So JavaScript only has one number type, which is great. It's often criticized that it doesn't have ints and those other things, but I think that's actually one of the brilliant strengths of the language. It means you avoid a large class of errors, and you as a programmer are much more effective because you're not wasting your time on details which don't add value. The only problem is it's the wrong type. And the reason it's the wrong type is because it has a binary basis, and a lot of the work that we do in JavaScript interacts with humans who are used to base 10, and so we're constantly throwing stuff at them which is wrong. So I mean to fix this. So this is my proposal for how we fix this. A new number type called DEX64 is a modern decimal floating point type. I recommend that DEX64 is the only number type in well-designed application programming languages in the future. Because if there's only one number type, you cannot make an error by choosing the wrong type. In a hardware implementation, DEX64 integers can be added in a single cycle, eliminating the performance justification for int. Numbers work the way that humans think numbers work. Elimination of numeric confusion reduces errors. Conversion of DEX64 numbers to text and back is simple, efficient, correct, and unsurprising. And DEX64 can exactly represent decimal fractions of 16.3 digits, which is more than adequate for all of the stuff that we do. So this is the format. It's really simple. It's a 64-bit word. There's a 56-bit coefficient, which is just an integer that's been shifted 8 bits up. And in the bottom 8 bits is a coefficient. Both are signed magnitude. And so the value of a number is the coefficient times 10 to the exponent. So the encoding is as simple as a floating point format can possibly be. 2 integers which combine in this formula to make a number. Really, really simple, really straightforward. There's a reference implementation in x64 assembly language that you can find on GitHub. Again, I think all future languages should be using this. So let's talk some more about numbers. So 0 divided by 0. What is 0 divided by 0? Any guesses? Well, it depends on who you ask. So most mathematicians will say it's undefined. And they don't mean the silly thing that JavaScript means by undefined. They mean that you can't even talk about this. You can't even think about this. This is not an imaginable, allowable thing. If you're talking about no, we don't talk about 0 divided by 0. There's nothing to say. It can't be said. Another says the machine should catch fire. The assumption is that no well-written program will ever divide 0 by 0, so it doesn't matter what happens because it'll never happen. And we know that's not true, right? If it's possible for a program to do something, it will happen. There's another argument that says it should be null or nan or some other sentinel value which says, it didn't happen. That's a reasonable thing. There's another argument that says it should be 0 because in business processing, 0 is actually the correct answer. You know, if we sold 0 units this quarter and our profit this quarter was 0, how much is the average profit per unit? You know, you can't say, boss, shh. No, 0 is obviously the right answer, right? There's an argument that says it's 1 because n over n is 1. I once worked on a machine where the answer was 2. It was a control data machine built or designed by Seymour Cray, maybe the best computer designer in history. And I can imagine a conversation that happened at control data. One day someone came to Seymour and said, Seymour, we found a problem with division. He said, well, what's that? He said, if you divide 0 by 0, you get 2. He said, so? Shouldn't we fix it? Look, no one's going to write that. It's not important. A correctly written program should not depend on what 0 divided by 0 is. And subtract is already the most complicated, slowest operation on the CPU. In order to fix this, I'm going to have to add more circuitry and add another cycle to something that's already the slowest thing, which will slow down all programs written by people who are not idiots. So I'm not going to fix it. And as far as I know, I'm the only person who ever saw it. So why do I care about that? Well, not so much do I care about 0 divided by 0. I'm more concerned with this case, 0 times n. What is 0 times n? Any guesses? Mathematicians would say 0. That's absolutely the right answer. It doesn't matter what n is. N could be infinity, doesn't matter, it's 0. Just, it can't be anything else. In fact, infinity isn't a value. Infinity is a metaphor that you can't really multiply by infinity. So, correct answer. But the designer of the IEEE floating point standard, which is the one that JavaScript uses, says, well, actually, if n is nan, then the result is nan. Even though I think mathematically that's indefensible. It doesn't make sense. So why is that an issue? Well, the first generation of compilers were written by people who assumed that n times 0 is 0. So if at compile time they can determine that they've got a multiplication in which one of the factors is known to be a 0, they don't have to execute the other thing if it doesn't have side effects. In fact, they don't even have to generate code for it. And so not only does the program get faster, the compiler gets faster. Everything gets improved. Except when this crappy floating point thing came out, suddenly those compilers were now in error because they now have to go ahead and generate that useless code anyway just to check for the chance that it might have been a nan, even if it was unlikely to be a nan. And so that slows everything down, and I don't like that. So why does this matter? Who writes code like that? Well, not a lot of humans write code like that, but machines do. So code generators, macro processors, partial evaluators, multiplication by 0 happens very commonly. Also, there are now non-conditional idioms, because one of the slowest things that CPUs can do today because of the massive pipelining that they do is conditional branches. So there are cases where you can replace a conditional branch with multiplication by something that might be a 1 or a 0, and then adding those two possible things together, that can go much faster than a conventional if structure. So there are performance reasons for why we would like 0 times n to be 0. So I believe that in a well-designed computer number system, all of these forms should generate 0 regardless of what n is. And DEC64, in fact, has this property. They all work like that. So that brings me to the end. But before I go, I want to thank you, of course, but there are also some other people who I really need to thank. Unfortunately, they couldn't be here this morning because they're dead, but I still feel that I need to thank them. So first, I want to thank Leonardo Fibonacci of Pisa. In the late 12th century, he visited Arabia. He's from Italy, obviously. You can tell from the hat. He met with the Arabian scholars and mathematicians there and learned about the amazing things they were doing using the Hindu numbers and the things they were doing in geometry and algebra and algorithms. And he brought all of that stuff back to Europe, wrote a book which basically taught Europe how the Arabian number systems worked and added a lot of contributions of his own. He taught the Italian bankers how to compound interest, which generated so much wealth that it funded the Renaissance. So thank you for that. Then Gottlieb Leibniz, a German mathematician and philosopher. He invented the calculus, so big thank you for calculus. He also was the first to come up with the idea of using 2 as the basis of the number system. He anticipated some of the things that we might be able to do someday with computers. That informed the work of George Boole, a German mathematician who, working in Ireland, came up with a system of thoughtful reasoning based on the values of 0 and 1. Our Boolean type is named in honor of George Boole, so thank you. Then Boole's work was discovered by Claude Shannon, who found that there could be a direct mapping between Boole's logic and digital circuits. And so all computer systems today are designed on principles that Shannon discovered based on the work of Boole. So that was great. And if that weren't enough, Shannon also came up with a theory of information which determined that we could translate any analog signal into a digital signal and back to any desired degree of precision, which is an amazing thing. This is what makes the digital age happen. That comes all directly out of the work of Shannon. So thank you very much for that. And finally, I want to thank Tahuti. I couldn't find a photograph. This was the best picture I could find. Tahuti is the guy who invented writing. There's some people who think it was actually written or invented in Iraq, but I think it happened in Egypt. This is a guy who worked out the rebus principle, which showed that we've got pictures which we can identify with the sounds. We can use the pictures for those sounds and spell things that are difficult to represent as pictures. This is where all writing begins. All writing starts with the rebus principle. And this guy was the first guy in the world to have figured that out. And so how do we know that he's the guy who did it? Well, he invented, well, in any religious tradition, sometimes they'll write, and it was written. So who did the writing when it was written? Well, in Egypt, it was the scribes. The scribes were the students of Tahuti. And when they write the religious texts for Egypt, they include Tahuti in those stories. They elevate him into a god. So he becomes the god of writing and magic. So why did they do that? So most of the stories that they're writing, they're old stories, they're centuries old at least, and they're just writing down stories. There had never been a god of writing before, so that was a new invention because they were the first writers. So why did they do that? I think they did it for two reasons. One was they wanted to elevate their own profession, that this is something that the gods do, something the gods care about, and we're doing that work. And so it kind of puts them in a profession which has some stature, some recognition, some status. Also, I think it was their way of giving thanks to Hootie for allowing them to have the best jobs in Egypt. They didn't have to go work in the fields, they didn't have to haul the rocks, they didn't have to catch the fish, they just got to squat and write and count and add up stuff, and it was great. So you, all of us, are the sons and daughters of Tahuti. We turn numbers into magic. Thank you. So we have a little time for questions. Yes?
So do you have a version of the deck for that works on, sensors, things that where memory really is?
Currently, there is one implementation of DEC 64, which is for the AMD 64 line, which is what's in PCs. It could easily be written for ARM processors and other things, but I haven't done that yet, and I'm hoping someone else will do that because I'm working on a book.
Do you have a thought about how you would make it fit with
Memory generally is not an issue anymore. That Moore's law has been so incredibly generous on memory capacity that to a first approximation, it just doesn't matter. Anybody else? All right, thank you.